We're going to learn about something called the Gram-Schmidt process. Before we can talk about the process, though, we need to say what it is we're talking about here. And so we need to describe something called an orthonormal basis. So you've seen bases of vector spaces before, right? A regular basis is a set that is linearly independent and spanning. But now we're going to impose another restriction on it in order to call it an orthonormal basis. And this new restriction here is that anytime you take two vectors in your basis, they're going to be orthogonal, and each vector is a unit vector. Now I want to point out that this is actually not some weird, strange property here. If you were to look at your standard basis for, say, R2, these vectors here are perpendicular. They are the x and y axes, and each one has a unit length. And you've seen in other math classes that using x-axis and y-axis, it was pretty useful in a lot of different problems. And in fact, when you use specifically the 1001, it simplifies a lot of application problems on this. So the idea of a basis being an orthonormal basis is actually a pretty useful thing to have. And so we're going to want to be able to do that here. But the problem is that not every basis is going to be orthonormal. We saw an example before where the basis, or the set 1, 2, 3, 4, you can prove that those are linearly independent, and you can prove that they are spanning. So therefore that means it is a basis. The problem is that it's not a particularly convenient basis. It would not be very easy to use that to solve a problem. And so we would like to learn how can we get an orthonormal basis, which is useful, but we also want to have something more than just the standard basis. We'd like to be able to do things in different directions when a problem calls for that. And so that's what we're going to see in this video. And what the Gram-Schmidt process is going to do, it's going to show us how to take any old basis and turn it into an orthonormal basis. Okay, now before I get into the actual formulas for the Gram-Schmidt process, because it's kind of a big mess at first, and only really by repetition do you kind of get it down and understand what things are going on here. If you just try to look at the formula, it's a big mess. So to try to help us out here, let me say the notation here. U's are going to be the vectors that you start with. Those are the original vectors in the problem. V's are going to be the vectors after you've turned them into orthogonal vectors. So at that point in time, they're all going to be perpendicular to each other. And then the last one, the W's, are going to be your final answer. That's after you turn your V vectors into unit vectors. So here's how the process starts. We go ahead and say, okay, my first V vector is going to be the same as my first U vector. What I mean by that is whatever vector you have listed first in your set, you are going to use that as your first direction. And then what you're going to do after that is you're going to make sure that any next vector has to be perpendicular to that. And the way we're going to do that is by this formula, which may seem very odd at first, but I want to kind of point out this thing right here. This is the vector projection of the vector u2 in the direction v1. Now I'm going to draw a little picture right here. I'm going to have the vector v1. I'm going to have my second vector in my original basis u2. And then what happens here is when I calculate this proj here, what that means is draw this right triangle and ask yourself how far out do you have to go in the direction of v1 before you line up with u2. That is exactly the vector projection of u2 in the direction of v1. That's what projection vector means. It means this picture right here. And what happens is, if you take your u2 and you subtract this thing, well, by vector subtraction here, we're going to get this part right here. And that is going to be perpendicular to the original vector v1. And that's how we're going to guarantee that they're all perpendicular to each other. We're going to say start with the vector we're given and subtract off whatever we need to make it be orthogonal or perpendicular. And then when we have harder ones or later vectors in there, we subtract off all the different projections to make sure it's perpendicular to all the individual previous vectors. It's kind of a mess here, but this is what we do. And you just keep doing that forever until you get to the last vector. Once you've gotten all the v's calculated, that means all your vectors are going to be perpendicular. And if you want to make them unit vectors, you just divide by each of their lengths. Now let's do an example here where we have R3. So I give you a basis for R3. This is definitely not the standard basis. I'll remind you what the standard basis for R3 is. That's the x, y, and z axes. But in this problem, for some reason, we care about these directions more, and so this is what we're going to do. So that means these vectors are our u1, our u2, and our u3. We first find our v's. The first v is always the same as the first u, 1, 0, 1. My second v is going to be my second u minus the projection of the second u onto the first v. Well, my second u is 1, 1, 1. Now, previously I used this notation here for the inner product because this will work in whatever inner product space you have. But right now we are working in R3, which is our normal dot product. So that means I would have 1, 1, 1 dot product with the original v1 over the length of the original v1 times the original v1 here. And we're going to get 1, 1, 1 minus, and we can do a little bit of work here. It's going to be 2 over 2 times 1, 0, 1. And if you do all of that, you're going to get 0, 1, 0. So that's going to be our second vector in our new orthogonal basis. We have to do one more v calculation. You take your original third vector, which is negative 2, 5, 2. You subtract off the projection, which is negative 2, 5, 2, with the first direction v1. And then you also subtract off the projection in the second v, which is going to be 0, 1, 0. And if we do a little bit of work here, the first dot product there is going to be 0, which means you're not going to subtract off anything there in the first dot product. In the second dot product, you're going to have the result 0, 5, 0. And so when you subtract here, you're going to get negative 2, 0, 2. And these are your three v vectors that are all perpendicular. And so then if you want to go ahead and make them normal or unit vectors, you can divide by their length. And if you look at the first one here, it's going to be length root 2. The second one is actually already a unit vector. And the third one, do a little bit of algebra there, it's going to be negative 1 over root 2, 0, 1 over root 2. And so here is going to be your orthonormal basis starting from the basis that was given to us. And this is the process you're going to use whenever you're trying to create an orthonormal basis. Now, we aren't really going to see it in our class, but having an orthonormal basis is very useful in a lot of applications of this. In particular, there's a very popular application of this concept called Fourier series that is used in physics and engineering and a lot of different circumstances. In fact, Fourier series is one of the most applicable topics in math, in my opinion, but it's really more for an upper division class, not this one, and so I'll leave it here. But again, if you want to read more about it, and in case you weren't sure how it's spelled, this is how you spell Fourier series. And this is all kind of going behind the scenes when you're doing Fourier series.